You're welcome to another wonderful FUTO Fun Club tutorial. My name is Kings and I'm working in collaboration as always with Colgate and Landmark, and we are working on the platform of Show Great Tutorials, FUTO, the greatest university in Africa. Really, you can't beat it, man. Okay, let's face the facts. We're here to discuss the topic on physics, and that topic is electric current. Electric currents. Okay, before we talk about electric current, let's just actually see what happens in a DC circuit, in an electric circuit. A circuit actually comprises of a battery. This is a battery that has a positive terminal and a negative terminal. These are the two terminals of a battery. So actually, when you connect a wire from the positive terminal to the negative terminal of a battery, actually electrons flows from this terminal through the wire. It flows to the positive terminal, and conventionally, okay, this is electron, they flow from the negative terminal of the battery to the positive terminal. And conventionally, positive charges, electrons and negative charges, we believe that positive charges, actually Q, flows from the positive terminal to the negative terminal. So current I also flows from the positive terminal to the negative terminal. So if we have an electric wire, if we just take a section of the electric wire, let's just take from this part to this part. We're just trying to cut this part off so we can actually examine that section at this point. This is the enlarged section of that part of the wire. So this is the cross-sectional area. And this is the length of the wire. From this point to this point is the length of the wire, the short wire we actually took. And normally electrons flows from this part. These are the negative charges. They flows, this is the negative terminal of the battery. It's connected to this point, and the positive terminal of the battery is connected to this point. So electrons, which are negative charges, flows from this part to towards the positive direction, and positive charges, actually these are positive charges, they flow from the positive point to the negative part of the battery. So we actually have lots of charges moving in and out of the wire. So what is current? Current actually takes the direction of the movement of the positive charge. This is current moving in the same direction, opposite the direction of the electron, and in the same direction with the positive charges. So current is actually equal to the charge divided by the time. And what do we mean by that? Positive charges actually flows from, okay, let's just say this is the continuation of the wire. This is the continuation of the wire. Remember, we actually cut this section from here. So positive charges flows. These are the flow of positive charges. They flow into this cross-sectional area and flow past this cross-sectional area and go to this other part of the cross-sectional area. So the total amount of charge that passes through this cross-sectional area, this point to this point, divided by the time it takes that amount of charge to cross through that place, is the current. So current is actually equal to charge divided by time. So if you were asked the question that a charge of 5 coulomb, a charge of 5 coulomb flows through a wire for 5 seconds. Oh yes, let's just say 5 seconds. What is the current? What is the current through the wire? The current is simply the charge, which is 5, divided by the time, which is 5 seconds, strikes off to be equal to 1 ampere. the unit of current is actually ampere. We might actually have smaller currents which might be in milliampere, which might be in microampere. You know, milli is divided by 1000 and micro is divided by 1 million, something like that. So actually the current, the unit for current is ampere. So this is an equation you should actually take at heart, that current is equal to charge divided by time. Okay, what if we want to express this current in terms of electrons, in terms of the whole charges that goes, the whole activities and the charges that works inside this piece of wire? Now you're gonna get what point I'm trying to make right now. The charge, the total charge that's actually passing through this surface area, the total charge passing through this area goes from this point to this point. They move from this point to this point. So if this charge completes a distance of length L, this is the length from this point to this point, and the charge moves, they actually move in crowd. The positive charges, they move in crowd. So before the first one to get into this cross-sectional area gets to this part of the cross-sectional area, the whole volume is filled up with charge. The whole volume of this wire is filled up with charges. So the total charge divided by time, the total charge will be equal to the total charge in this volume. The total charge will be equal to the total charge in this volume. So if we want to express that charge, we have to take note of a point. We have to take note of a point called the charge electron density. Electron density. We have the sign for electron density is N, and it's equal to electron divided by volume, the number of electron per unit volume of a wire. So the total number of electrons, would be equal to the electron density times the volume of the wire. So the total electrons in this volume of wire, the total of electrons in this volume of wire is equal to N multiplied by the volume of the wire, So, but we are actually trying to get the total number of charge in the wire, not in the volume of the wire, and not the electrons. So we convert these electrons, we convert the electron to charges by multiplying it by a factor, 1.6 1.6 times 10 raised to the power of minus 19. This is actually the charge in one electron. So if we multiply it by the total number of electron, it gives us the total number of charge in the volume. So we would like to write this value in a simpler form. So we can say the total charge is equal to N V Q. The Q is actually representing this charge of one electron. So this is the total charge in the wire. And if we actually want to find the current in the wire, we say this value divided by time. That gives us the actual current through, because the current is the total number of charge that passed through this cross-sectional area to this point, and the time it takes to complete that distance. So we want to actually split this volume into a simpler form. So we say the charge is equal to, let's just write this Q first of all. We have Q, then we have N, then volume is actually equal to area multiplied by length. So the volume is the cross-sectional area, multiplied by the length. That gives us the volume. So if we're asked what is the current, through a piece of wire, and they gave us the electron density, they gave us the area of the wire, they gave us the length of the wire, and we know Q. Then we can simply say the current is equal to Q N A L divided by T, because this is charge divided by time. So you shouldn't actually consider this formula yet, because we are still trying to drive into a particular point which I want to pass on to you. So I want you to know that these charges moving from this part of the area, this cross-sectional area to this cross-sectional area, actually moves with a particular velocity. They move with a velocity, and that velocity is called the drift velocity, Vd. And drift velocity Vd is equal to length divided by time, distance over time. That's drift velocity. So the length of this wire L and divided by the time it takes to complete this length, to move from this point to this point, that is the drift velocity. So the length, if the drift velocity is equal to length over time, then the length should be equal to the drift velocity multiplied by time. We simply just multiply the time with the drift velocity. So we can actually use this value for length and replace it with this part of the equation. So the current actually becomes, we say the current was, okay, let's just write it here for people not to get confused. The current was I equals QNAL divided by T. Right. Now the current becomes equal to QNA, since L has become drift velocity multiplied by time, we replace it. V drift velocity multiplied by time divided by time. So this is the current, and if time strikes off time, then we have that current is equal to Q, which is 1.69 10⁻⁻⁹ 19, multiplied by electron density, multiplied by the area of the wire, multiplied by the drift velocity. So this is the formula you should take at heart. We've actually brought out two important formulas on current. We have the first formula, that current is equal to charge over time, and the second formula, that current is equal to QNAVD. So if you might be asked a question, to find the current, and you were given bread and milk and sugar. You were given the drift current density, you were given the area of the wire, you were given the drift velocity, and you were asked to find current. You simply just put all this together, punch it, and get your current. So right here we've actually gotten two formulas for current. Let's clean this one up quickly. And we talk about another point. The first point is current is equal to charge over time. The second point is current is equal to QNAVD, drift velocity. The next point you have to know is the current density. The current density is written as J. Some places write it as I, but really the current density is J. And current density is simply equal to the current divided by the cross-sectional area of the wire. That gives us current density. And if current is equal to, let's say, if current is equal to QNAVD, then the current density should be equal to QNAV, that is a V, D divided by what? A, area. So if this one strikes off this one, then we have that current density is equal to QNVD. So drift velocity multiplied by electron density multiplied by Q, which is charge, 1.6 times 10⁻⁻⁹ gives us current density. Or current density gives us could be I over A. So you take up these two formulas. So we've actually gotten four formulas right now, the formula for current, the two ways of getting current, this way and this way, and the two ways of getting current density, this way or that way, depending on the actual quantities that were given to you. You actually use the correct equation to find your current or your current density. Okay, if we have a wire, a piece of wire, and current is flowing through this piece of wire, for current to flow through this piece of wire, there must be a potential difference, and that potential difference is written as V. V actually is the potential difference. So for the potential difference and the current is actually related in this way. The potential difference and the current is related in this way, but actually there's something in the wire that actually obstructs or tries to stop the flow of current, and that is the last factor in this relationship, R, and this R is called the resistance. The resistance is trying to resist the flow of current. So this relation we actually have here is called the Ohm's law. The Ohm's law states that the voltage is equal to the current multiplied by the resistance. Every wire has its own resistance, but the resistance in some wire changes with different factors. Like if this is a wire, it might have a resistance of R1. Some factors might affect this piece of wire and it will now have a resistance of R2. Let's just list those factors down. But before we list those factors down, I want you to take this formula important. I want you to just actually try to take this this formula. I want you to take this formula as if it's gonna help you in some kind of crazy question in your examination. Actually, I didn't know how to express myself there, but this formula is quite important. V is equal to IR. So if they give you voltage and they give you current and they tell you to find resistance, you simply just make resistance the subject of formula, you make R the subject of formula, and use your V and I to find R, just vice versa that way. So we're trying to talk about the factors that actually causes the resistance of a wire to change. The first factor is the length of the wire. The length of the wire, actually the more the length of the wire, the more the resistance of the wire. And another factor is the cross-sectional area. The cross-sectional area of the wire. Another factor is temperature. The temperature of the wire. The temperature. The more the cross-sectional area, the more the more the cross-sectional area, the less the resistance of the wire. And let's see. The next one is temperature, and the next one is the type of wire, the nature of the wire. The nature of the wire. So these are the factors that affect the resistance of a wire: the length, the area, the temperature, and actually the nature of the wire. So this length, area, and temperature, they actually have a kind of equation that binds them together. That equation is I'm not going to talk about the equation for temperature right now, but the equation for length and area is actually resistance is proportional to length over area, the cross-sectional area. But there is a factor that changed that proportionality sign to an equality sign, and that factor is called the resistivity of the wire. So resistance is equal to resistivity multiplied by length divided by area. So this is another formula. You might be asked to find the resistance of the wire. They gave you the resistivity, they gave you the length, they gave you the area. They might not even give you the area. They might give you the diameter or the radius of the wire, and you have to find the area from that fact, and you can just mix all of them up to find the resistance of the wire. So if you also have to know that the resistance, the resistivity, if we make the resistivity subject of formula, the resistivity is equal to the resistance multiplied by area divided by length. So this is the resistivity. It's just making resistivity the subject of the formula. But actually you can find the conductivity of the wire. The conductivity of the wire is written as sigma is equal to the inverse of the resistivity. So you might be given the area of a wire, the length of the wire, and the resistance, and you might be asked to find the conductivity instead of the resistivity. So the answer you get as the resistivity, the inverse of that answer is your conductivity. So 1 over resistivity is conductivity. So that is another point. No, I just want you to note this equation. Just believe me, I was trying to teach this in one of my classes and the students almost stoned me to death. They hated me because they say the equations, the formulas are too much, but really they're not too much. We've just gotten like 4 equations for current. We've gotten 4 equations for current, this one, this one, this one, and this one, and we've gotten like the 3 equations for resistance and resistivity, and we've gotten 1 equation for conductivity. So they're not much. Then I'd like us to have to actually find the relationship between resistivity, conductivity, electron current density, and the rest of them, electric field, blah 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 blah. So how do we find it? We say we're trying to get another relationship. We say resistivity is equal to resistance multiplied by area divided by length. Right. Okay. And we know that V is equal to IR, so resistance will be equal. Resistance is equal to V over I. So anywhere we see resistance, we can majestically change it to V over I. So from this formula we have right here, we can change this resistance to V over I. So resistivity is equal to V divided by I. Okay, divided by I multiplied by, nope, actually there's a mistake, V divided by I, which is the resistance, multiplied by A over L. So we've not done much but replace this resistance to V over I. So we then have that resistivity, okay, let's just reshuffle the equation. We take I to this point, I multiplied by resistivity divided by A is equal to V divided by L. So we simply took I to this point and we took A to this point, and that gave us I over A. Okay, so if we could remember, we told you that current over area is current density. So current density J multiplied by resistivity is equal to V over L. V over L. Remember back in the topic electric field, electric potential, we say that electric field multiplied by length is equal to electric potential. So electric potential, electric field should be equal to electric potential divided by length. If you could remember, I actually did it in a previous topic, electric field, electric potential. That was the topic we did this. So we can simply replace V over L with electric field. So equals electric field. So current density multiplied by resistivity gives us electric field. And also, if this one is coming right here, if this is coming right here, it becomes current density is equal to 1 over resistivity multiplied by electric field. And we remember that 1 over resistivity gives us conductivity. So current density is equal to conductivity multiplied by electric field. So this is the last equation for here you have to take note of. So we've actually found the equation that current density is equal to conductivity multiplied by electric field. Current density multiplied by resistivity is equal to electric field. And electric field, nope, we found out that conductivity is equal to 1 over resistivity. We found out that electric resistivity is equal to resistance multiplied by area divided by L. And these whole equations are very easy. They're very simple to prove. The essence of knowing how to prove these formulas is, in case you actually forget one of the formula in your examination, you can simply run through the proving to get each and any of them. They are just logical and they're straight to the point, and very soon we're going to be using them to solve equations, very interesting equations which are not very complicated. For the meantime, you just have to hold on for the equation.
Gangnam Style. Gangnam Style. Op, Oppan Gangnam Style. Gangnam Style. Oppan Gangnam Style. Sexy lady. Oppan Gangnam Style. Sexy lady. Being no. 오빤 강남스타일. 오빤 강남스타일.